Hello, my name is Daniel Hudson, and I'm presenting the third lab of Physics 2212, where I focused on the magnetic dipoles. In this experiment, a smartphone downloaded a magnetometer, which is an app that detects the magnetic fields from a bar magnet. So the phone was placed in a few different positions and orientations. First, the field was measured on axis to determine the relationship between distance and field strength. Then the phone was turned perpendicular as shown in this image to determine the change in the magnetic field at that orientation. And finally, the phone was moved upwards to measure the magnetic field at an angle of 45 degrees off axis. A few of the fundamental physics principles involved are outlined in these equations. The first is the distance dependence equation, which shows that the magnetic field is dependent on the distance to the object. So we use this to determine the relationship between the two, and that n value will be calculated using our data. The magnetic field of the dipole is given by this equation, which is the relationship between the magnetic moment and distance. And we will calculate the magnetic moment as well from data. And finally, the magnetic field of the dipole is given by this equation to the right, which allows us to determine the magnetic field at any point in space around the dipole. So the data and results show a correlation as expected, where as distance increases, the magnetic field decreases. This correlation is by a linear slope of -3 between the two logarithmic factors, which shows an inverse relationship of 1 over distance cubed. So our n is equal to about -3. From there, I was able to plug the values given here into the on-axis dipole equation to get a magnetic moment of about 2.61 amperes per meter squared. The computational model was based mainly on this equation down here to the right, which is the magnetic field at any point in space. I was able to calculate the different strength of the dipoles at the different effect of the dipole at the various locations, and plot an arrow corresponding to the magnetic fields. So the orange represents the location when the location's on axis, the direction of the magnetic field to the right, and when the object is perpendicular to the magnetic field or to the bar magnet, we can see that the magnetic field points to the left, as represented by the blue arrows. The small pink arrow here at the top right is an object at a 45-degree angle, and we can see that the magnetic field points up and to the right. I then used the computational model to compare to some experimental values, where I calculated the distance between the object and the magnetic dipole, the magnet, to be 0.254, and that was pretty similar to what was given by the computational model. However, the magnetic field differed pretty significantly, specifically in the x-coordinate. This could be explainable by just a number of other magnetic factors interfering with the experimental setup, and which was not included in the computational model. So the number down here on the left might be a more pure representation of how magnetic dipole works. So some final questions before I leave you. If the phone had not been laid out at true north, what would have happened? More than likely, the magnetic field from the Earth would have interfered with some of my calculations and results. So without compensating for the true north. And then finally, what would happen if a second bar magnet had been added? I would expect that there would be a small increase to the magnetic field, likely not a large one, but the introduction of a second magnet would probably create a larger magnetic dipole moment, which would lead to a bump in the strength of the magnetic field. Thank you for watching.